Hi, welcome back to Classical Mechanics by Unify Physics. Let's continue discussing a little bit more into Lagrangian dynamics. So today we'll discuss what's called as Noether's theorem. It's actually a connection between symmetry and conservation. Actually, we have already seen a special case of this, which we called cyclic coordinate. We said that if a coordinate is cyclic, or if a coordinate is cyclic, then there's a corresponding conserved quantity. We called it the conjugate momentum. For example, if theta is a cyclic coordinate, which means theta does not appear explicitly in the Lagrangian, then the conjugate momentum corresponding to the coordinate theta would be conserved. So if theta is an angle, this conjugate momentum would be an angular momentum, and if this coordinate, the cyclic coordinate, if it's like x, then the corresponding linear momentum would be conserved, etc. So we have seen this already, and we have already said that this is a special case of more general theorem called Noether's theorem. Today we'll discuss the Noether's theorem from the viewpoint of Lagrangian dynamics. So it appears everywhere. This Noether's theorem is very important in modern physics. It appears everywhere. Today we'll discuss it from the framework of Lagrangian dynamics. So we'll discuss symmetry and conservation and the theorem called the Noether's theorem, and then we'll do a couple of problems. Now, so I think we can start by doing a problem. The Lagrangian of a system is invariant to first order in the small number epsilon under the change qi going to qi plus epsilon ki. So the thing is that here the coordinates are being changed by a small quantity. And this epsilon parameterizes the small quantity, so it changes, and each coordinate changes. So if you have x, y, and z, this means that x would go to x plus epsilon k1. Generally, it could be a function of x, y, z also. So let's y would go to y plus epsilon k2, and z would go to z plus epsilon k3. So if you make this transformation, and if the Lagrangian is invariant up to first order, so the change in Lagrangian up to first order is 0. Up to first order means up to first order in epsilon. So if you take the transformed Lagrangian and subtract the old Lagrangian from the transformed Lagrangian, and if there are no quantities proportional to epsilon in this subtraction, then we say that it is invariant up to first order, but we'll see this in detail. So this is given. The Lagrangian of a system is invariant to first order in the small number epsilon under the change qi goes to qi plus epsilon ki of q. Then which among the following is a conserved quantity? Which among the following is a conserved quantity? So let's see how we can do this. Now how do we demand that the Lagrangian does not change up to first order? One way to do is that let's find the transformed Lagrangian. The transformed Lagrangian would be, we can say that, the old Lagrangian, we write it as epsilon of qi, qi dot, and t generally. The transformed Lagrangian would be L of qi plus epsilon ki, qi dot plus epsilon ki dot, t. Now we need to demand that, as given in the question, we need to demand that the Lagrangian is invariant up to first order. So what we do is that we take L of qi plus epsilon ki, qi dot plus epsilon ki dot minus L of qi, qi dot, t. We find this difference. And if there are no terms, if in this difference, if there are no terms up to first order in epsilon, then we say that the Lagrangian is invariant up to first order. Now the one way to do this is to get the Taylor expansion of this. Make a Taylor expansion about this qi dot. So you'll get you can write it as L of qi plus qi dot, t plus the first order, second order terms in epsilon, etc. And subtract L from it, and if the first order terms are 0, you demand that the first order terms are 0 and see if there is a conserved quantity. That's what we need to do. Now there's an easier way to do this. We could simply take dl by d epsilon is equal to 0. dl by d epsilon is equal to 0. It's equivalent. So this thing is equivalent to this. We can either Taylor expand this and find the difference, and demand that the first order quantities are 0, the first order terms in epsilon are 0, which means in this expansion we don't include the terms proportional to epsilon, okay, or we demand that that's equal to 0. It's equivalent to saying that dl by d epsilon is 0. All right. Now at home you can actually try this method, okay, just to convince yourself that it is exactly the same. You make a Taylor expansion, okay, and demand the term proportional to epsilon is equal to 0. Okay. So that's not very difficult. When you make a Taylor expansion, you choose only terms up to the first order, because we are not worried about the higher order terms. I'll just give you a hint. You can do it as a homework, okay, just to convince yourself that it's exactly the same. Okay. So this, if you make a Taylor expansion of this, this would be L of qi comma qi dot comma t, okay, plus you will get since there are n number of coordinates here, you'll have a summation over I, okay, and you say dou L by dou qi multiplied by epsilon ki, all right, plus there's also a term from here, so you'll have to do summation over I dou L by dou qi dot multiplied by epsilon ki dot, that's the first order term, okay, right, minus this term, okay, we are retaining only the first order term in epsilon, minus L of qi comma qi dot comma t, all right. Now this cancel, and this is the first order difference. Now we demand that this is equal to 0, okay, you demand that this is equal to 0, okay, we could do that, and I just want you to know that it's equivalent to doing dl by d epsilon is equal to 0, okay. So when you make dl by d epsilon is equal to 0, you try the other method. So if you do dl by d epsilon is equal to 0, we say that 0 is equal to, okay, we'll put the summation outside. So we are taking a derivative with respect to epsilon. So this is dou L by dou qi and multiplied by dou qi by dou epsilon, okay. This we are just using the chain rule, because L is a function of qi dot and t, okay. So we are demanding that the first order change is 0. That's why I write 0 here. So dou L by dou qi by dou epsilon plus dou L by dou qi dot by dou epsilon, okay. So that's it. We are demanding that this is equal to 0. All right. Now what's your new Lagrangian? Your new Lagrangian is actually qi going to, it corresponds to the coordinate change qi going to qi plus epsilon ki, okay. So this dou qi by dou epsilon, okay, this is the new coordinate. So dou qi by dou epsilon is equal to actually ki, okay, that's equal to ki. So this is equal to summation over I, so dou L by dou qi by dou epsilon, so dou L by dou qi multiplied by ki plus dou L by dou qi dot multiplied by ki dot, okay. So this is equal to 0. Okay, this is what we are going to demand now. Okay. So here this q, so this is actually the transformed Lagrangian we are talking about, okay. This is the transformed Lagrangian with the coordinates transformed by this factor, okay. Now what do we do now? So we can write this as, this is dou L by dou qi ki, dou L by dou qi dot k dot. So we can write it like this. This is summation over I. So from Lagrange's equation, we know that Lagrange's equation says that dou L by dou qi is equal to d by dt of dou L by dou qi dot. So we'll just write this dou L by dou qi as d by dt of dou L by dou qi dot, okay, multiplied by ki plus ki dot is equal to 0. All right. So I'm just demanding that the first order change is 0. Okay. Now what do we have here? You see that now we can write this as a total derivative, because you have got d by dt of dou L by dou qi dot and dou L by dou qi dot ki dot. So we can write using the product rule. Okay. We can write it using the product rule, and we'll simply write it as d by dt of summation over I, okay, dou L by dou qi dot ki, is equal to 0. Okay. So we are demanding this is equal to 0. So 0 is equal to d by dt of. So you can check this, all right. So if you make an expansion using the product rule, you'll get d by dt of dou L by dou qi dot here multiplied by ki plus dou L by dou qi dot ki dot. Okay. So we see that the time derivative of some quantity is 0 if we demand that the first order change in the Lagrangian under this transformation is 0. All right. So if the first order change in the Lagrangian is 0, it means that there is a quantity which is conserved. All right. So the conserved quantity here is because d by dt of something is 0. This means that this is a conserved quantity. It does not change with time. Conserved quantity. Okay. So the conserved quantity is summation over I dou L by dou qi dot ki. Right. We can call this as a conserved momentum, but it need not have the dimensions of momentum. So this is the right answer. Okay. It's dou L by dou qi ki. Okay, this is the conserved quantity. Okay. So as I said, you can also find it from here. It's just one more step from here. So this is slightly, it has one or two more steps here. Okay. So because what I've done here is that I've made a Taylor expansion and this terms cancel, and we are demanding that this term is equal to 0. Okay. So there's a common epsilon here. We can remove it and you'll again get the same thing. Summation over I dou L by dou qi ki plus summation over I dou L by dou qi dot ki is equal to 0. It's exactly the same thing. So if you want to demand that the first order variation is 0, you just take dl by d epsilon. Okay. It's exactly the same thing. All right. So we have done it in two ways and we have got the result as option A. So we can say that the quantity P of q comma q dot, we define it like this, summation over I. Did I write some? Yeah. So summation over I dou L by dou qi dot ki of q is a conserved quantity, does not change with time. Does not change with time. Okay. So that's a conserved quantity. All right. Now this is actually Noether's theorem. This is actually one formulation of Noether's theorem. Okay. The case of cyclic coordinates is a special case of this. We'll see. Okay. As we'll soon see, the fact that when there's a cyclic coordinate, there is a conserved momentum. Okay. That's a special case of this rule. So it's the general expression for the conserved quantity. So the theorem actually says that, Noether's theorem actually says that, we'll just write it down. For each symmetry of the Lagrangian, there's a conserved quantity. Okay. For each symmetry of the Lagrangian, we have a, or there is a conserved quantity. Okay. So what do we mean by symmetry? Okay. Generally, symmetry means that you do something to the system. Okay. You translate it or you rotate it. You do something to the system and the Lagrangian does not change. Okay. That's called symmetry. That's a full symmetry. But for Noether's theorem to work, okay, it's Emmy Noether. For Noether's theorem to work, you don't need a full symmetry. You need only to demand that the Lagrangian does not change up to first order. Okay, it can have second order changes and still we will have a conserved quantity. So symmetry generally means that the Lagrangian does not change when you make a change to the coordinates. That would be a symmetry. But okay, but here for Noether's theorem to work, you don't need to have a full symmetry. You need only to have the Lagrangian invariant up to first order. Okay, invariant up to first order. All right. So in this case, symmetry means the Lagrangian has no first order change in these quantities. All right. So here we mean that by symmetry we mean that if the coordinates are changed by small quantities, the Lagrangian has no first order change. Okay, first order change, which means that in the new Lagrangian there are no terms proportional to epsilon, if epsilon is the small quantity. No first order change. That's sufficient for Noether's theorem to work. So even if there is a full symmetry, as in the case of cyclic coordinates, then also Noether's theorem works. But for Noether's theorem to work, you need only a first order invariance to the Lagrangian, okay, when you make a small change. I hope that's clear. Let's do so that's Emmy Noether. Okay, yeah, I have it written here. So for each symmetry of the Lagrangian, there is a conserved quantity. Symmetry means if the coordinates are changed by some small quantities, the Lagrangian has no first order change in these quantities. Okay, by conserved quantity we mean a quantity that does not change with time. All right. So as I said, I am repeating here, the conservation of momentum conjugate to cyclic coordinates is a special case of Noether's theorem, and this is Emmy Noether. Okay, and Emmy Noether was a mathematician, a very important person for physics. Okay, all of modern physics is actually based on primarily or mainly based on Noether's theorem. Okay, Noether's theorem is very important in general relativity or in particle physics. Everywhere this relation between symmetries or how we can actually deal with symmetries, it's very important. Okay, that's why I have put a photo of her here, because she is such an important person for all of physics. Okay, now let's look at an example. Okay, we are talking about a ball thrown upwards. The Lagrangian for a ball thrown upwards is given by this. Okay, this is the kinetic energy and that's the potential energy. We take the height along the z direction. Okay, find the conserved quantity. Find the conserved quantity. All right. Now we already know that here there are two conserved quantities. Why? Because you see that y and z, y and x and y are cyclic. Okay, x and y are cyclic coordinates. So this for this problem we can actually identify just by looking at this Lagrangian, because x and y are cyclic. So we know that dou L by dou x dot and dou L by dou y dot are actually conserved momenta, conserved quantities, conserved momenta. Okay, but let's do it using Noether's theorem just to be familiar with this method. So we look at this Lagrangian and we ask what are the symmetries. Okay, what are the symmetries? So we say that we can change x by this quantity, x going to x plus, let's call it epsilon k1. Okay, x going to x plus epsilon k1, and k1 is some constant, it could be anything. We can take it as 1, for example. All right, so we can write as epsilon kx. Okay, and y remains the same. That's one symmetry. Okay, there's another symmetry, x remaining the same and y changing from y to y plus epsilon k. Let's write it as ky. Okay, now this kx and ky can be any constant. We'll choose it as 1. Okay, you'll see that we can choose any constant and they all are conserved quantities, but we'll take the simplest possibility for this. We can take kx and ky as 1. So we'll first deal with this symmetry. This is one symmetry transformation, this is another symmetry transformation. Okay, so in this symmetry transformation we have got kx equal to 1 and ky is equal to 0. Okay, this ky is equal to 0. All right, or maybe we can write it in a slightly better way. We'll write the transformations as x going to x plus epsilon kx and y going to y plus epsilon ky. Okay, this is symmetry transformation. Now there are two symmetry transformations that we can talk about. One symmetry transformation is this: we take kx equal to 1 and ky is equal to 0. That's a symmetry transformation. And the second symmetry transformation we'll write as, okay, we'll take kx equal to 0 and ky is equal to 1. So corresponding to each of this, we'll get a conserved quantity according to Noether's theorem. And what does Noether's theorem say is the conserved quantity? It says that we can say P1. Okay, the first conserved quantity is P1 using this relation. Okay, that's dou L by dou x dot kx. Okay, what was the conserved quantity? It was summation over I dou L by dou qi dot ki. That's a conserved quantity. That's Noether's theorem. Okay, so here the coordinates are x, y and z. So it's dou L by dou x dot kx plus dou L by dou y dot ky plus dou L by dou z dot kz. Okay, what's kz here? Kz is 0, because if you change z, the Lagrangian actually changes. Okay, so we can take this z going to z plus epsilon kz. We can just add that here. So kz has to be 0 in both cases. Okay, so these are the two symmetries. Now we substitute kx equal to 1, ky equal to 0, kz equal to 0 in this. So this is equal to dou L by dou x dot kx equal to 1. So that's then ky equal to 0, kz equal to, so that's p1 is dou L by dou x dot. Similarly, you will get p2 is equal to dou L by dou y dot using the same relation. Okay, so you just in the second case, you just kx equal to 0 and take kz equal to 0, and you'll get dou L by dou y dot. Exactly, this is exactly the same thing that we found using the fact that x and y are cyclic. Okay, so I just wanted to show that this is a special case of Noether's theorem. All right. Okay, now if you have this thing, okay, p1 and p2, as I said, we chose kx and ky to be 1 and 0, etc. So instead of 1, you could take 2, no problem, because then if p1 is conserved, then 2p1 is also a conserved quantity. There's no problem. All right. So we can consider this as simplest quantities, okay, or some sort of basis. So if p1 and p2 are conserved, then 2p1 is conserved, 8p1 is conserved, or 3p2 is also conserved, because if p1 is conserved, dp1 by dt is 0, then 2p1 is also conserved. Or we can have an infinite number of conserved quantities, because combinations such as 2p1 plus 3p2, these are also 0, because if you take d by dt of this, okay, since these 2 and 3 are constants, you will simply get 0 again. Okay, so this p1 and p2, you can consider it as some sort of a basis set of conserved momenta, and there are an infinite number of conserved momenta that you can construct from this. Okay, so I hope that is clear. All right, let's discuss another problem here. We have got a Lagrangian. The Lagrangian is given like this, and we are supposed to identify the conserved momentum. We'll use the Noether's theorem, as I said, as we discussed so far. So what do we have here? Okay, so here we see that in the previous problem we had cyclic coordinates. All right, the symmetries were obvious just by looking at Lagrangian. Here it's not so obvious because there are no cyclic coordinates. Okay? We have got x and y coordinates, so system is moving in a plane, in the xy plane. So but we don't have any cyclic coordinates. We have got both x and y here. All right, so still we have to identify a symmetry here in order to find a conserved momentum. How do we identify the symmetry? So we said that if we were talking about symmetries of the kind qi going to qi plus epsilon ki, okay, qi plus epsilon ki. All right, so this means that we can change all the coordinates at the same time, and the combined transformation of all these coordinates can lead to a symmetry transformation. For example, we can do this x going to x plus epsilon kx and y going to y plus epsilon ky. We can make two different transformations to x and y and see if it is a symmetry of this Lagrangian. Okay, so by looking at this, by inspection, we see that if we make x going to x plus epsilon, all right, and then y going to y plus 2 epsilon, then this is a we see that the combined transformation, okay, this combined transformation is a symmetry transformation. Okay, you can easily check this. So this is merely by inspection, because there's a 2 here. I added epsilon to x, all right, there's minus y here. So I'll have to add 2 epsilon to y, so that these extra terms will get cancelled off. We can check this easily. What happens when x goes to x plus epsilon and y goes to y plus 2 epsilon? We see that x going to x plus epsilon will become this term. All right, we'll just check this term, because these terms are all derivatives, time derivatives. So this constant change does not do anything there. Okay, this part is already symmetric, no problem. We'll just check this term. So what happens under the transformation x going to x plus epsilon? Then 2x will become 2x plus epsilon. Okay, and what becomes of y? Y becomes y plus 2 epsilon, because that's the transformation that we are talking about here. And what happens to this combined term? 2x minus y becomes 2x plus epsilon, 2x plus epsilon minus y plus 2 epsilon. So we see that these terms get cancelled. So this is equal to 2x minus y. All right. So we have seen that this transformation is actually a symmetry transformation of the Lagrangian. Okay. All right. So this is again a full symmetry. Okay. As I said before, we don't need a full symmetry for Noether's theorem to work, but if there is a full symmetry, then Noether's theorem works. All right. So this is a symmetry. Now we can find the conserved quantity by Noether's theorem, because Noether has taught us that the conserved quantity is this. It is dou L by. So if the symmetry transformation is this, ki going to ki plus, qi going to Qi going to Qi plus epsilon Ki. If this is a symmetry transformation, then summation over I dou L by dou Qi Ki. This is a conserved quantity. Alright. So here we see that there is a 1 sitting here. This is 1 multiplied by epsilon and 2 multiplied by epsilon. Okay. So this K1 is a constant 1, or Kx is a constant 1, and Ky is a constant 2. Now we can identify the conserved quantities using Noether's theorem. Okay. The conserved quantity, we just make the summation. Okay. Since our coordinates are x and y here, we will do dou L by dou x. Sorry, dou L by dou Qi dot. Sorry, there's a dou L by dou Qi dot here. So it's dou L by dou x dot K1 or Kx. Kx is 1. Okay. Plus this is the conserved momentum that we are talking about. This is dou L by dou y dot. And what is Ky? Ky is 2. This is your conserved quantity. Okay. Now you just have to take the derivatives here and simplify. You see that this becomes m. Okay. M multiplied by 5x dot. Okay, because there's an x dot square here, and this, when you take the derivative, this 2 will get cancelled with this 2, etc. So this is 5x dot. There's an extra 2 here. So this is minus y dot. Okay, this is dou L by dou x dot multiplied by 1 plus dou L by dou y dot. What's dou L by dou y dot? Dou L by dou y dot is again we can see from here, it's equal to m multiplied by we get minus x dot from here, okay, because we have cancelled this 2 with this 2, minus x dot plus 2y dot. Okay, plus 2y dot. Don't forget this Ky now. Okay, don't forget this factor 2. This is your conserved quantity. Now we can easily simplify this because we have got a 5x dot here, minus 2x dot, that becomes 3x dot. So that is m multiplied by 3x dot plus 3 y dot, because we have got a 4y dot here and minus y dot, so it's 3y dot. Okay, so this overall factor 3 is not important. So this means that the simplest conserved quantity that you can talk about is P is equal to m multiplied by x dot plus y dot is a conserved quantity. If this is a conserved quantity, then 3 multiplied by this also is a conserved quantity. So we can say, you can, depending on what is given in the options, you can choose the correct answer. Okay, you can find the conserved quantity. The conserved quantity will be a multiple of this term. Okay, m x dot plus y dot. It's possible that they give in the option something like 10 m x dot plus y dot. Of course, this is also a conserved quantity. Okay, so that's how we use the Noether's theorem. In this case, it will have the what do you say? It will have the dimensions of a linear momentum. Okay, dimensions of linear momentum. All right. Okay. All right. Let's now discuss energy conservation. Okay. And as I said before, Noether's theorem says that corresponding to every conserved quantity there is a symmetry, or corresponding to every symmetry there is a conserved quantity. In classical mechanics, you can say it in either ways. All right, corresponding to every symmetry there is a conserved quantity, and corresponding to every conserved quantity there is a symmetry. Right, we know that energy is conserved. Energy is one of the famous conserved quantities, one of the important conserved quantities in physics, and the corresponding symmetry. All right, so by Noether theorem, we can identify that the corresponding symmetry is actually time translation invariance. Okay, time translation invariance. So the conservation of linear momentum is associated with spatial translation invariance, or symmetry under a spatial translation, and energy conservation is associated with time translation invariance. All right. So if you translate the Lagrangian in time, and if it remains invariant up to first order, then we can say that the energy is conserved. The energy of the system is conserved. All right. And similarly for rotation, so if the system is symmetric under rotation, then we say that the angular momentum is conserved. All right. We'll be coming back to the formulation of Noether's theorem in different contexts, okay, later on. So now we are doing it in the Lagrangian dynamics framework. All right. So this is the question. We'll start with the question. If L has no explicit dependence on time, that's dou L by dou t is equal to 0, then which among the following is a conserved quantity? We could answer this question if you know it, or we can just try. Okay, so if you don't know exactly which the conserved quantity is, the only thing we have to do is you take the time derivative of each of this quantity and check if it is equal to 0, provided this condition is satisfied. Okay, we can check the first quantity. Okay, we can check dE by dt for the first quantity, and we'll get d by dt of 1 to n, and here we have qi dot, okay, maybe we don't need this, yeah, minus dl by dt. Right, you just distribute this derivative inside. Okay, and what do we see here? Here we can use the chain rule, so this becomes summation I equal to 1 to n d by dt of dou L by dou qi dot multiplied by qi dot. Okay, all right, minus plus the product rule. It is, I'll have the summation pulled outside, and this becomes dou L by dou qi dot qi double dot. Okay, so first you take the derivative of the first term multiplied by the second term, then the first term multiplied by the derivative of the second term. That's a product rule. Okay, all right, minus dl by dt. We can also expand dl by dt because L is a function of, okay, if you look here, L is a function of qi dot and t. All right, so what is dl by dt? You have to use the chain rule. All right, so if you use if you find dl by dt, that's dou L by dou qi dot. Okay, because the Lagrangian can change because of the dependence of qi on time. Also qi dot can depend on time, and the Lagrangian can change accordingly. That is dou L by dou qi dot qi double dot. All right, this is the change in the Lagrangian due to the change in qi dot with respect to time. And there's another term here because this is an explicit dependence. This is dou L by dou t. All right, so dl by dt is dou L by dou qi dot plus dou L by dou qi dot qi double dot plus dou L by dou t, and there's a summation over I. Okay, there has to be a summation over I. Okay, that's it. So this becomes, and this summation I think we can pull outside because it's the same summation. We don't have to write it all over again. So that's equal to minus, we'll write as dou L by, I think I'll give a bracket here, dou qi dot plus dou L by dou qi dot qi double dot. Okay, that's inside the summation, and since it's minus here, I'll write this outside, minus dou L by dou t. Okay, so dE by dt in this case is this. Right, now if you look carefully here, this is d by dt of dou L by dou qi dot. Am I right? But from Lagrange's equation we know that dou L by dou qi dot is equal to, sorry, dou L by dou qi, this is the Lagrange's equation, dou L by dou qi is equal to d by dt of dou L by dou qi dot. Okay, so we see that the coefficients are the same here, qi dot, and the Lagrange's equation says that d by dt of dou L by dou qi dot is equal to dou L by dou qi. So these two terms cancel. Okay. So we see that these terms also cancel, dou L by dou qi dot, qi double dot, and dou L by dou qi dot, qi double dot. These two terms also cancel because there's a minus sign here. Okay. All right. So this says that dE by dt is equal to, if you are taking the first option, dE by dt is equal to minus dou L by dou t. All right. So again this result. So the first option says that if dou L by dou t is equal to 0, then the E given in the first option is a conserved quantity. Okay, what was that E? So we say that we checked the first option, which was given as E is equal to summation over I equal to 1 to n dou L by dou qi dot minus L. Okay, so we conclude that E is equal to summation of I equal to 1 to n dou L by dou qi dot minus L is a conserved quantity provided dou L by dou t is equal to 0. So when you say dou L by dou t is equal to 0, it means that the Lagrangian has no explicit dependence on time. Okay. So corresponding to this symmetry, corresponding to symmetry that the Lagrangian has no explicit dependence on time, we get a conserved quantity, and this conserved quantity we call the energy. Okay, we can check that this is actually the energy of the system for some cases. Right? So this is the energy of the system. We can actually check this. Okay. All right. Okay. So we can check this. Right. So for example, we take a simple case of Cartesian coordinates. So the total energy you can write as half mx dot square plus y dot square plus z dot square, the Lagrangian, minus v of x comma y comma z. So you see that this Lagrangian has no explicit dependence on time, which means that there is no time t floating around in the expression for the Lagrangian. There can be an implicit dependence because x, y and z are generally dependent on time. Also x dot, y dot, z dot are generally dependent on time. But there is no explicit dependence on time. There is no term like at or something sitting here. Okay, that's what we mean when we say that Lagrangian has no explicit dependence on time. Okay, so here this is the Lagrangian, and what's E corresponding to this? Okay, let's check the E corresponding to this. So we say that E is equal to summation over I to n dou L by dou Qi dot minus L. Okay, so we'll just do it here, and what do we get? What's dou L by dou Qi dot? So there's a summation over that. So you do dou L by dou x dot plus dou L by dou y dot plus dou L by dou z dot. Okay, and what we get is half m. Okay, dou L by dou x dot is 2x dot, and you multiply it by x dot, so it becomes 2x dot square, plus similarly 2y dot square plus 2z dot square, minus what was the Lagrangian? It is half m x dot square plus y dot square plus z dot square minus v of x comma y comma z. Okay, all right. So that's equal to, you see that this 2 and this 2 get cancelled, and you see that this is equal to m x dot square plus y dot square plus z dot square minus half m x dot square plus y dot square plus z dot square. Okay, so this minus and minus will get, this is plus v of x comma y comma z. And what is this? This is equal to half m x dot square plus y dot square plus z dot square plus v of x comma y comma z, which is nothing but the total energy. This is the kinetic energy plus the potential energy, the total energy. All right. So we see that for some cases this is actually the total energy that we are familiar with. All right. So summation over I dou L by dou Qi dot minus L is the conserved energy of the system. All right. Now, now we have to be a bit careful here. The quantity that we are discussing here, all right, this quantity, it's the total energy of the system, total conserved energy of the system only. Okay, we have to be careful only when the entire system is like represented by this Lagrangian. Only this is the total energy only when the entire system is represented by L. Alright, so if it's only a part of a system, if it's interacting with something else, then this cannot be the total energy. Alright, so but dE by dt, this relation will always hold. dE by dt equal to minus dou L by dou t will always hold. Alright, but it need not be the total energy unless you are talking about the closed system. Alright, the whole system. The Lagrangian is representing the total system. If it's not a closed system, then this is not the energy. You have to be a bit careful here. If it's not a closed system, this is not the total energy. Okay, all right. Okay, so with that, I think we can conclude today's class. So here I have written it down. So the quantity that we discussed so far, what's this quantity under discussion? It is summation over I dou L by dou Qi dot, all right. This gives the energy of the system only if the entire system is represented by the Lagrangian. All right. The Lagrangian must represent a closed system with no external forces. If the system is not closed, then the equation, this may be valid, but E may not be the energy of the system. All right. So in a simple case, we have shown that this gives you t plus b in the case of Cartesian coordinates. All right. So with that, I think we can conclude today's session. what we discussed is the connection between symmetries and conservation laws. We saw that earlier we had seen that if there is a cyclic coordinate, then the corresponding conjugate momentum is conserved. Here we have seen a more generalized version of this. If the system has any symmetry under the change of coordinates, the symmetry, by symmetry we mean that it needs to have only a first order if it needs to have only first order symmetry, which means that if you make some changes to a coordinates and the Lagrangian does not change in the first order, all right, then it leads to a conserved quantity, which we called as the conserved momentum. We saw that a change, a translational symmetry gives conservation of momentum, a rotational symmetry would give conservation of angular momentum, and there is also a connection between energy conservation and time translation symmetry. If the system is invariant under a time translation, all right. So if the system is the same now and tomorrow, or today and tomorrow, then we say that the energy is actually conserved. Okay. All right. So with that, we'll conclude this session. I'll see you in the next class. Okay. Thank you.